Ooh,
Okay.
got it.
Okay, welcome again to the European Non-Associative Algebra Seminar. It's a pleasure to introduce the speaker of today, Professor Willem De Graaf from the University of Trento. The title of his talk is Computing Galois cohomology sets of real reductive algebraic groups. Please, Willem.
Yes, thank you. So I hope you can all hear me. If not, then please complain. So I'm going to report on an ongoing project with Mikhail Borovoi from Tel Aviv, which is about computing, well, as the title says, computing Galois cohomology sets of real algebraic groups, real reductive algebraic groups. So first, a little introduction to this topic. First, maybe why do we want Galois cohomology at all? And as I see it, well, I say here's one of the main problems in algebra, which I mean from my point of view. Maybe there are 100,000 other main problems in algebra, but at least this is an important one. Is if you have a group G acting on a set X and determine the orbits of the G on X. If we could do that in general, then we could solve many problems. Okay, so this is certainly an important problem and has been studied in many contexts. And I'm certainly not going to solve it. Just an example. If we take a field and take the group GL and F, which acts by conjugation on the nilpotent n by n matrices over F, then you can consider several fields. And if you look at your normal forms, for example, over the complex numbers, you immediately get a classification of the orbits. And next question could be, what happens if you take the field equal to the real numbers? Of course, this can be solved in many, or I don't know many, but in a few ways. But in any case, this is a typical situation where Galois cohomology can come in to help. Yeah, because the group and the set on which it acts depends on the field, and we know what the classification over the complex numbers, and we want the the classification over the real numbers. Okay, and to give another example, so as I said, this matrix example can be solved. Well, I think I at least know of two ways to solve this. But here is another example of another project with Mikhail Borovoi, and that time also with Hong Van Le, where we classified the orbits of SL9R acting on the wedge 3 of R9. And there the orbits had been classified over C by Wienberg and Elashvili in 1978. Well, they published it in 1978. And we did the real version of that using lots of Galois cohomology. Okay. So that is the first motivation for Galois cohomology. The next slide is about what it actually is. Well, Galois cohomology is a rather big subject, and here we only do Galois cohomology relative to the Galois group of C over R. So these examples that I just did are sort of typical for what we do. We know the classification, the orbit classification over C, we want it over R. So we are only interested in the Galois group in this context of C over R, which is the, well, it's the smallest group that there is, right? It's just a group of two elements. Okay, and what is the general situation? We have a script G, which is a group on which this gamma, this Galois group, acts by automorphisms. And this action you should think of as a kind of complex conjugation, okay? And we denote it like this. So G goes to gamma G. Yeah, so the only action is of interest is the action of the gamma. The one acts as one, so that's nothing happening there. And the gamma has a kind of complex conjugation. Okay. And an element of such a group G is called a cocycle if G times its conjugate is equal to 1. Yeah? And the set of all cocycles is denoted Z1 of G. And on the Z1 of G, we can define an equivalence, which is as described over there. It's a kind of twisted conjugation. So G1, two cocycles, G1 and G2 are equivalent. Not if one is conjugated to the other, but one is conjugated to the other when we put a gamma on the second factor, right? So G2 is h to the power minus 1 times G1 times the conjugate of h. So it's almost conjugation, but not quite. And the set of all equivalence classes is the first Galois cohomology set, which we denote H1 of G. Okay, and now this is a rather mysterious thing, this cohomology set. Of course, this is defined like this, but what it actually is, if you have a concrete group, is not so easy to see. And in fact, it is also just a set. Okay, it doesn't have a structure. It's not a group. It's not a vector space. It's, well, in general, in any case. Yeah. But it always has a special element, which is the class of 1, right? Because 1 is a cocycle, therefore it has an equivalence class, and that's the special element of the H1 of G. And for this reason, it's sometimes called a pointed set, which means a set with a special element. Okay. Now, and what does Galois cohomology do? Just briefly, what it does actually doesn't play any role in the rest of the talk. I just want to show it to motivate the study of these things. Sorry. So now we have our script G again, which is the group, and it acts on a set X. And both the Galois group gamma acts both on the set X and on the group G, such that the action is compatible. So the conjugation of G acting on X is the conjugate of G acting on the conjugate of X. So we have such a situation. Okay. Now let's take an element in an X naught in X that is stable under conjugation. We say that it is real, right? So its complex conjugate is equal to itself, to X naught itself. Therefore, it's real. And we take its orbit. So we are interested now in classifying real orbits. So we start with the real element. But we take its complex orbit, and we are interested in the real orbits contained in this complex orbit. Okay. And for that, we take the stabilizer of this X naught in the group G. And now I think I have to introduce a little piece of notation. If I have a set S on which gamma acts, we set S gamma as the set of all things that are fixed under the conjugation. All things fixed under the group gamma. Then, because the stabilizer is a subgroup of G, we have a natural map of the H1 of the stabilizer into the H1 of G, which just maps the class of a thing in the first set to the class of the same thing in the second set. No, there's no, it's quite natural sort of thing. Doesn't do anything basically. And then we have a theorem by Borel and Serre that if we look at the orbits of the real group, let's say, the fixed points under gamma, on the fixed points in the orbit y under gamma, those orbits are in bijection with the kernel of this I star. Okay. So how do I classify real orbits? Well, I start with all real points. I take their complex orbits, which somehow I know from the complex classification. I take these stabilizers, I compute their Galois cohomology sets, I compute these kernels, and then I know all real orbits contained in all complex orbits, and so I know all real orbits. So that's more or less how it goes. Of course, this is not so easy because otherwise, well, there wouldn't be a problem. But anyway, this bijection, so the bijection of the theorem works as follows. So if I take a cohomology class in the kernel of I star, how do I get to its orbit? Well, because it lies in the kernel of I star, there is a G in G with this property here. Fine. And then the orbit corresponding to the class has a representative G acting on the X naught. Okay. So, and the typical situation where we can apply this is where G is a subgroup of GL and C acting on a complex vector space V, and the action of gamma is complex conjugation. Then we have this situation. So the okay, and to give another example on which I recently worked, just to make a bit more publicity for my own stuff. If you take the group G, which is SL2C in the power 4, acting on the 4-fold tensor power of C2 in this way. And well, then the group fixed under gamma is just SL2R to the 4th, and V gamma is the 4-fold tensor power of R2. Okay, and in recent work with Heiko Dietrich and Alessio Marani and Marcos Aurilia, we have classified the complex orbits, so over C, which is of interest in quantum information theory, and using heavily Galois cohomology, we have also classified the real orbits, and that's of interest in high energy theoretical physics. And one of our co-authors, so Alessio Marani, is a physicist, so he knows all about these sort of things. Okay. Good. And well, main result, what I want to talk about, or results, or outcome, let's say, of our project, is if I have a subgroup in GL and C, a reductive algebraic group defined over R, that means that G is defined by polynomial equations in the entries, and the polynomials, they have coefficients in R, so real coefficients. And we have an algorithm for computing the H1 of G. Okay. And what is the input? So this is, of course, the series of seminars on non-associative algebras, and so far I've only been talking about groups. Associative algebras come in as the Lie algebra of this group G. So as input to our algorithm, we assume we have a basis of the Lie algebra of G. And this basis is given by n times n matrices. Okay, so that's the basis. And now there are basically two situations where that can happen. G is either connected or it is not connected. If it is connected, then I'm happy just with the basis of the Lie algebra. If it is not connected, then I also need to know the component group. So then I need a finite number of elements of the group that are representatives of the cosets of the component group. And I also need to know the group structure of the component group along with the induced conjugation action on the component group. So that's, and the non-connected case is much more difficult than the connected case. But anyway, I will come to that. So one remark in our application, so the few examples that I gave that we're interested in are actually reductive. That's of course important. If I can only do it for reductive algebraic groups, I bet I have, if I want to apply this to our problems, then the groups have to be reductive. Okay. And for the action of gamma, we usually consider the normal conjugation on the matrix entries. So you just take the complex conjugates of matrix entries. But we also consider maps of the form where an element G is mapped to C G bar C in the power inverse, where C is some co-cycle in GLN-C and normalizing G. So some conjugation by normal conjugation, if you like. Well, yeah. Okay. This will not really play a role in the talk, but anyway. Now, some earlier work in a 2018 paper, Adams and Taibbi listed the order of H1G for G simple algebraic groups. Apparently these orders can also be computed with the so-called Atlas software. So there is a software developed by Adams and many other people, which is called the Atlas of Lie groups, if I'm not wrong. And apparently you can compute this, but it's not described in the manual, so I still have to figure out how to do that. But in any case, for our applications, we need, as we've seen before, we need explicit elements of the Galois cohomology sets, because we needed to do then to make this explicit correspondence with the orbits. Okay, good. Oh, is that the next slide? Yes. Okay. So now so if there's questions, please shout. Yeah, I'm happy to ask questions or to be interrupted or anything. If not, then I just go. And the algorithm is sort of slightly complicated, and I will not give all details. And there are several cases to consider. A base case is the case of a torus. And what is a torus? A torus is a connected algebraic group that is diagonalizable. Okay, and this case, I will look at this case in a little bit of detail. So in this case, my group is called T for torus. And it's connected and diagonalizable. And diagonalizable means that I have a matrix C, such that C times T times C inverse consists of diagonal entries. And we know a basis of its Lie algebra. Okay. And we want to compute the H1 of T. Okay, for this we first have a look at how to compute in this group T. So we just know a basis, I repeat, a basis of its Lie algebra, but we want to compute in the group. Okay, and this works well with tori. This works very well, apart from a little problem that I will not talk about. Maybe I can mention it, but it works very well because tori, they are sort of they're very intimately connected to lattices in Z to the n, and with lattices in Z to the n, we can compute very easily, or well, very easily. I mean, there are many algorithms for computing with them, so they're easy is maybe another thing. So what we do is we have our Lie algebra T there, and we diagonalize also T. So we have the same matrix C, such that the Lie algebra T is diagonalized by it. And then we look at all integral vectors that are relations of the eigenvalues, sort of linear relations of the eigenvalues of the elements of the Lie algebra. Okay, so the E1 to En such that is some EI alpha I 0, where the alphas are eigenvalues of elements of T. Okay, and that's a lattice lambda in Z to the n. Now, given our Lie algebra, we can compute this lambda. Well, we can compute this lambda if we can diagonalize this T, right? And that is usually not a problem. If your T is very nasty, you need a very big field extension to diagonalize T to represent the eigenvalues, then computationally this may become very difficult. But usually if the input is sufficiently nice, this is not a problem. Okay. Then the diagonalized group, so C times T times C inverse, it consists of this. It consists of the diagonal matrices such that the eigenvalues on the diagonal satisfy more or less the same relation, but now multiplicative. Yeah, so the product of beta I to the EI has to be 1 for all elements in the lattice. Of course, for these relations, I can take just the basis of the lattice if I want. Then I get so. So I can characterize the from the Lie algebra, I can characterize the elements of the group. Okay, but we want some more, and we want to work with. We want not only to characterize the elements, we want to work with them. And what we then do is the perp. We compute the perp lattice, which consists of all vectors that are perpendicular to all vectors in my original lattice lambda. Yeah, I call that lambda perp. And if I take an element in lambda perp, and I define this lambda m of t over here, which is for a complex number t is just t in the power m1 till so diagonal matrix with diagonal entries t in the power m1 to t in the power mn. Then this is an element of c times t times c in the power inverse. This is an element of this diagonal group. That follows from the description of the c times t CTC inverse given above. Aha, so this way I can make elements of this group. And even more, if I take a basis of this lambda perp and I do it for every basis element, and then I take different arguments t1 till td, and I take the product of all that, then I get an isomorphism of the non-zero elements in C to the power D, to my diagonal torus. Okay, so from the Lie algebra, I can compute this isomorphism. And this now gives me a very good way of computing with elements of the torus, because I can represent them by D tuples of non-zero complex numbers. Okay. And now we come to a thing which is called writing T as a product of standard tori. And here I cannot go really into details because that would become very technical. But the point is this: such a torus, so our groups, they have this complex conjugation, right? The action of the group gamma. And now in this case, in the case of the torus, you can represent this conjugation by an involution of z to the d. I'm not going to say exactly how to do that, but the conjugation corresponds to an involution of z to the d. And then we can compute the basis of this z to the d with the following property, that the first k basis elements are mapped to minus themselves. Then we have L basis elements which are mapped to themselves. And then we have pairs of basis elements that are interchanged. Okay, we can compute such a basis. And then using this basis, we can compute another isomorphism of C cross to the D to our T, such that, well, if I act with the conjugation on such an element, I get mu. The first k arguments are, the argument is conjugated to the -1. Then in the next L argument, the argument is just conjugated. And in the remaining ones, the arguments are interchanged, which corresponds to this interchanging of the bases. And of course, they are conjugated. Okay, so this corresponds to writing T as a product of standard tori. And there are three types of them. One is just C cross, where the conjugation is Z goes to Z bar to the -1. The other one is C cross with normal conjugation. And the last one is C cross squared with conjugation interchanging the two elements and putting a bar over them. And the point is that computing the H1 of each of these standard tori is very easy. And since our torus is now a product of the standard tori, it's very easy for that as well. Right? So this means that the H1 of T consists of these classes, the mu of epsilon1 to epsilon k. So the first k basis elements were mapped to minus themselves, and the rest are all ones.
where the epsilon i's are plus or minus 1. So you get 2 in the power k elements. Yeah. Okay, this can be done in this can be done concretely. Yeah? So all this can be done concretely. So you get an H1 of 2 in the power k elements. Okay. Now we know how to do it for tori. We go on to connected reductive algebraic groups. So connected. No. And we know a basis of its Lie algebra, again, which is now called G. Then what we look at, the conjugation also acts on the Lie algebra. And we look at the real Lie algebra, which consists of 6 points. So that's the real form of the old Lie, of the Lie algebra of the group. Well, since it's reductive, we can write it as a semi-simple part times a central part, or plus a central part in this case. And some years ago, with Heiko Dietrich and Paolo Fachin, we devised an algorithm to compute a Cartan decomposition, a so-called Cartan decomposition of this real Lie algebra, real semi-simple Lie algebra, which is SR is equal to K plus P, where K is a maximally compact subalgebra. Okay, so we can do that. And what we do is now we take in this compact subalgebra, we take a Cartan subalgebra, which we call T0, and we take its centralizer in G. Then this T, the centralizer in G, is a Cartan subalgebra of G. And T0 is the Lie algebra of a maximal compact torus T0 in G. So T0 corresponds on the group level to a maximal compact torus, and T corresponds to a maximal torus. Okay. Then we consider a group W0, which is a subgroup of the Weil group. So we take the normalizer in G of this maximal torus T modulo T. That's the Weil group. So that's some very standard construction. And it's isomorphic. It's canonically isomorphic to the Weil group of the Cartans of the root system, I should say, of the root system corresponding to the Cartan subalgebra T. Okay. And now we take the subgroup W0, which is the normalizer in T0 modulo T, normalizer of T0 modulo T, which is the subgroup of W that consists of elements that leave this T0 invariant, or equivalently of elements that leave little T0 invariant, the Lie algebra, the Cartan subalgebra. Okay, so why do well? First, a little remark on how to get this W0. So W we know how to get because it's the Weil group of a root system. We can compute this root system and we can compute the Weil group. Now, using standard constructions, we can compute elements of G that induce elements of the Weil group. How does it work? Well, if you take the root system and you take a simple root alpha and you take x alpha, x minus alpha root vectors. So recall this G is the Lie algebra of an algebraic group, and the algebraic group is a subgroup of GL and C. So the Lie algebra consists of n times n matrices, and these root vectors, they are nilpotent matrices, just associatively nilpotent, so to speak. No? And so we can take their exponentials. And if you take this expression here, then we get something which is called W alpha. And such a W alpha induces the reflection corresponding to alpha in the Weil group. So the cosets of this W alpha, they generate the Weil group. So for each element of the Weil group, because I know I can do it for generators, I can do it for every element in the group, we can compute an element in G inducing it. I call this W hat. Then the W0 consists of those W such that the W hat conjugates this T naught into itself. Okay. So we can actually compute this W naught. And now we define an action of W naught on the H1 of T. So we consider the Galois cohomology set of this torus T, which, by the way, we know how to compute, right? Because of previous slides. And we define the right action of the group W naught on the H1 of T. And in the following way, we take an element W naught induced by W hat in the group G. If we take a Z in the H1 of T, so the T also lives in the n times n matrices. So this is just an n times n matrix, this Z. Then I can conjugate and put a gamma action on the second factor. And that's the right action. Okay, now we have to prove that this is well defined and so on. But this can be done. And there is a theorem of Borovoi, which he proved many years ago, but he published in a paper of 2022. That if you look at the natural map of the H1 of T in the H1 of G, yeah, because T is a subgroup of G, you get a natural map of the H1 of T into the H1 of G. This induces a bijection between the orbit space, the orbits of in H1 of T under W naught and the H1 of G. Right, so what I do is we compute the H1 of T, we compute the action of W, we compute all orbits, and for each orbit we take one representative, and that's the H1 of G. Ha. Okay. Oh, that goes, yes. So that's more or less how it works for connected groups. We do it, we take a, we know how to do it. First, we know how to do it for tori. Then we take a special torus, which is a centralizer of a maximal compact torus. Then we have this action, and doing this explicitly, we can then compute the H1 of G. Okay. I will later come to well, possible difficulties with this computation, but first I would briefly like to look at the case of non-connected G. This is just very brief because the technical details here become very long. So I will just give a sketch of how it works and more or less how we can proceed. So we suppose that G is not connected, and we look at the component of the identity, which I call G naught or G little circle. Yeah, that's the component. So there's a finite number of components, and one of these components has the identity in it, and that's the G naught. And we have the component group, which is the quotient of G modulo G naught, which has induced conjugation. And at the beginning, I said, or at the beginning, the start of all this development, I said that we know this C. We assume we know C, and we know its conjugation. So we can compute the H1 of C because it's a finite group. We can just do it by brute force. You just for every you compute all cocycles by checking every element and see if it's a cocycle. And then for each cocycle, you just compute its equivalence class, which are finite sets. So then you see how many equivalence classes you get. Okay. Now, the group G projects to C, right? Because C is a quotient of G. And that induces a map, the projection pi induces a map pi star from the H1 of G to the H1 of C, basically by mapping a class in the H1 of G to the class of pi of Z in the H1 of C. So that's a very easy map. But what we want is the inverse of this map. And that seems a bit daft. I want to compute the set G, and I make a map to something else. And then I say, well, I want to know all the inverse images. That's of course a very easy way of computing anything. You just make a map from your desired thing to something else, and then you take inverse images. Of course, the problem is how to get these inverse images. So you compute the H1 of C, and then for every element of H1 of C, you determine its inverse image. And then, of course, you have H1 of G. But why does this? Why does this? Could this strategy work here? That's because in the 60s, Borel and Serre have developed a theory that makes this work. So we use notation. We write sigma for the conjugation map. So sigma of G is gamma G now, right? So now sigma is more convenient. And because we want to change the conjugation. And we write H1 of G sigma means the first Galois cohomology set using the conjugation sigma. Okay. So now let's take an element in the H1 of C. And first we suppose that there is a cocycle Z0 in G. So we take our C0 in H1 of C and suppose that it lifts back into the group to a cocycle also Z0. So we suppose that they have a cocycle Z0 in G, so that the power of Z0 is equal to C0. Then we can define a new conjugation on G, which is twisted by the Z0. So we take the old conjugation and we twist it by Z0. Okay. Then we consider this new conjugation tau, and we write C tau for all elements in C which are fixed by this tau. Of course, tau can also be seen as a conjugation on C. Is just the induced conjugation. That's also acts on C, which is twisting by C0 essentially. So the fixed points on C acts on the H1 of the G0. So that's the connected component of the identity with respect to tau. So I take the first Galois cohomology of the identity component with respect to the new conjugation, and the C tau acts on that. And how does this action work? Well, I'm not sure whether I should go into detail here. Here's just the formula. It's not very difficult. It's a right action, and it's again a kind of twisted conjugation. Okay, and then there is the theorem of Borel and Serre that says if you have a set of representatives of the C tau orbits in the H1 of the identity component, then the inverse image of this C0 consists of those elements. You just multiply all elements with your Z0. Okay. So that's the theorem. So using this theorem, we can compute it. Well, we can compute the H1 of G0 because that's what we did before. Right? And if you have Z0, then, well, C tau is just a finite group. So then maybe we can do this. On the other hand, I suppose that there was such a cocycle Z0, but if there is no such cocycle, then the inverse image is empty. So then you can just discard it. So the big problem here remains: decide whether such a Z0 exists. And here we briefly look at how to do that, assuming that again that the G0 is a torus. So in the general case, we also have an algorithm, but that's very technical and rather difficult to explain. For a torus, it's sort of still, I would say, still digestible for such a talk. There is actually a small other problem, which I will not be talking about, that in order to compute these orbits, we need to decide whether elements in the H1 of the G0 tau are equal. So you get this H1 consists of classes, but we work with representatives of the classes. And if you get two different representatives, the question is, are they the same class? So we also need an algorithm to decide equivalence of cocycles. Now we have also an algorithm for that, but I will also not go into that, because also that is rather technical and well, it would take too long. But anyway, yeah. So there's quite a number of problems to be solved here. That's just what I wanted to say. So how to lift a cocycle? Now we suppose that we have a cocycle in the group C, in the component group, and we assume that our identity component is a torus. What do we do? Well, it's very short and simple. So we first lift C naught to something in G. We can do that. Now we can take an element that represents our C naught. And then we compute this element H, which is G naught times the conjugate of G naught. And then we define a new conjugation on G like this. Now we twist the old conjugation by G naught. And it's not so difficult to see that since the identity component is a torus, it's abelian. And actually, a thing that we also need is that a little h lies in the torus. This is again an involution on the torus. Okay, so we have new conjugation. And with respect to the new conjugation, we define a set B2, which is here, well, whatever it is. And it's not easy to see that the C naught lifts to a cocycle in G if and only if this H1 inverse lies in this B2. And how can we then decide this? We can decide this again by writing G naught, which is a torus, as a product of standard tori, as I did before. And we decided on the level of each little standard torus. And we sort of glue the answer then together to the big torus. Okay, so that's more or less how it can be done if it is a torus. Okay, yeah. So I will not go into the details here, but it's yeah. If you just look at this for 10 minutes, it's pretty straightforward. Now, to the last part of the talk. Probably finish a bit early. On implementation. So we have implemented the algorithm in the computer algebra system GAP4. Okay. Well, with a little twist. So a lot of twisting going around here, not only on the theoretical level. And the twist is that if I don't know if you have experience with GAP4, but GAP is not very good with field extensions. And for several steps that I haven't talked about, we need to take mth roots of field elements. Yeah, most of the time they are square roots, but sometimes there could also be cube roots, for example. But most of the time there's just square roots. But anyway, you take a square root, and maybe you need to get a complicated expression in the square roots, of which you have to take the square root, and so on. And you have to know whether that already lies in the field that you are constructed, and so on. Yeah. So GAP cannot do that, and I'm not how to say, I'm too lazy to write algorithms for that myself. Not only too lazy, but I'm not able. I'm not an expert in that sort of thing. So since experts have already done this for example, in SageMath, I just limited myself to writing a little interface to SageMath that took care of that sort of problems. Okay. The problem is that we then work over a field in GAP that we programmed ourselves, and that operations in that field can be very slow. Yeah? Especially if there's a lot of square roots around. Okay, yeah. Okay, so an example. SOPQ, which is connected. A connected example. The SOPQ is defined like this. You take this matrix IPQ, which is first you take the P times P identity matrix, and then you take the minus the Q times Q identity matrix, and that defines a bilinear form. And the SOPQ consists of all n times n matrices, where n is P plus Q, that leave this form invariant. So yeah. And the equations for an element for an n times n matrix to lie in this group are just the G transpose times the IPQ times G is equal to the IPQ, and well, the determinant you want. Okay, and its Lie algebra is this thing here. And it's not so difficult to figure out what the basis of the Lie algebra is. So SOPQ, and that basis serves as input to the algorithm. And then in the next table, I show some running times using two base fields. So in this case, we don't need because it's connected, we don't need to take square roots and things. That's because the square root things, they come up only when it's for the part of the algorithm where the group is not connected. So here are some running times. Yes. This is interesting. Okay. So these are the first column are the inputs, the input groups. These are the dimensions of the groups. Okay. This is the dimension of the torus T0. This was the maximal compact torus that played a role there. This is the order of the Weil group, which also played a role. I actually tried to replace that with the order of the Weil group W0, because that's. But anyway, this is the order of the H1 of G. So the output of the group is just a list of explicit n times n matrices which are co-cycles. Yeah? So the first one gives me 6 co-cycles, then I've got 7 co-cycles, and so on. Yeah? Which then represent the elements of H1 of G. And here we see the runtimes in the last 2 columns in seconds. The first field is square root field. That is our own homemade field, so to speak, which allows for taking square roots. And this is CF of 4, which is the cyclotomic field of degree 4, right? This is a gap internal field, which is taken care of in the kernel of gap very fast. And you see the running times over the CF of 4 is very much faster. So here we need something to the SO713. We need sort of like 20 minutes over the square root fields and about 34 seconds over CF4. Yeah? And time also goes into, time goes into also in computing, for example, a multiplication table of the Lie algebra, because the input is just, in this, for example, in this SO713, the input is just a list of 190, in this case, 20 by 20 matrices. And it needs to compute a multiplication table and maximal torus and, well, and so on, yeah? Cartan decomposition. All of these things. Also, you see that the size of the Weil group almost plays no role. Yeah. And that's because we use the Weil group as a permutation group, and gap is very good in permutation groups. So we have permutations, and also for the W0, the subgroup, we have permutations. Then we need to compute that, but it's not such a problem. And we have permutations, and we compute the action of these permutations on the H1 of T0. Sorry, on the H1 of T, really, which is the maximal torus containing T0. And then computing the orbits is for gap is very easy. So that's a good thing about gap. And the parameter actually which does play a role is this dim of T0 here, because that's the compact part of the torus. And as we've seen, that the size of the H1 of the torus is 2 to the power k. And in these cases, this is the k. So the H1 that we're acting on with the W0 will have a size of 2 to the power 14. And that's something like 16,000 or something. And the main running time of this, about 10 or 11 minutes that it takes, goes in computing the action on this 2 to the power 14 elements. So for each generator of the group and for each 2 to the power 14 elements, it needs to compute the image. And that takes a bit of time. Once that's done, it goes very fast. Okay. Next example is not connected. And there we compute the H1 of the automorphism group of the simple Lie algebra of type Dn. And the automorphism group is not connected. So its component group has order 6 if n is equal to 4. And order 2, sorry, if n is bigger or equal to 5. Okay, so what you get is basically the inner automorphism group plus a component group given by the diagram, the automorphism of the Dynkin diagram. And in this case, the H1 of Gn, so if I call it Gn, the H1 of Gn parameterizes the real forms of type Dn. So the real Lie algebra of type Dn. So we can actually check whether the answer is correct. And here are some running times. Well, here we have to take the base field equal to our homegrown field square root field because it's not connected and we very much need this square root machinery. And you see that the running times, they go up rather quickly. So for D4, where the group is of all the of dimension 28, well, this the running time was about, I don't know, a bit less than half an hour. For D5, it's almost an hour. And for D6, it's, what is it, 6 hours or something. So I didn't try D7. No? Okay. These are timings just done on my laptop. Maybe I could put it on some big server. But anyway, it's just to. The answer is known for Dn anyway, so I'm not going to. I'm not interested. I'm actually not interested in the answer because we know it already. Just wanted to show how the runtimes go up, and this basically is due to the non-connectedness. The connected part, so the algorithm for the connected part plays a very small part here. The main part is taken up by computing the action of this group C tau on the H1 of the G0. Because there, as I said, we need to then, every time we compute an action, we need to solve the equivalence problem of co-cycles, and that's again a difficult computation. So basically all the time it is testing equivalence of co-cycles. So that's where the time goes here. Okay, to finish some ongoing projects. Well, one ongoing project is to finish the paper that we're writing about this. And one thing that I wanted to program is because Mikhail Borovoi and Timashov in 2021 published a paper where they computed the H1 of G for semi-simple connected groups G using combinatorics of Katz diagrams. And that should be, well, that should be very, very fast. But of course, it's only for connected groups, but still, I think it's very worth the while to implement this. And but I still need to think about it. Okay. So that's one thing. And another thing, which is also a joint work with Mikhail Borovoi, and this time also with Adriaan De Graaf, is to do another classification, which is consider the groups GLMF times GLNF acting on modules of the form the wedge 2 of f in the power m tensor f in the power n, for f is equal to complex numbers and real numbers. And this leads then to a classification of two-step nilpotent Lie algebras of dimension 8 and 9. So that's again, connection to the classification problem of nilpotent Lie algebras. Yeah. Okay, so that finishes my talk. And well, thank you for listening.
Okay. Many thanks, Willem, for this interesting talk. Are there any questions, comments, remarks?
So I didn't catch. So what is the result about the original problem, right? You mentioned at the beginning, right? So there was this result of Ilashvili and Winberg, right?
Yes.
So then you said you want to consider this in the real case. So what is the result?
Ah, you mean well, this.
Yes.
The orbits of SLN9 are
Yeah,
at
yeah,
the of
yeah,
R.
yeah. Yeah.
So the result is an orbit classification. But
Okay.
it's rather I cannot sort of describe it. So this is so the Windberg-Elashvili thing is in the theory of theta groups. So they have lists of nilpotent orbits, and then some classification of semi-simple orbits, and then a classification of mixed orbits. And we have the same, but just over R. And it all expands a little bit. Yeah? There are many more, or there's quite a few more real orbits, and there are complex orbits. So it's so we have a paper. Yeah, it's on the archive, and it's also published in the Journal of Algebra. But you will see that if you look at the archive, we have two papers on the archive, one of about 30 pages and one of about 130 pages. And the 130 pages one contains all the computations and also a lot of Galois cohomology computations. And that was our motivation to write a program to do the Galois cohomology computations, so as not to have to do it by hand.
I see. I see. Okay. So, but this is like the description, just like in set theoretic way, right? No, not in any sense like algebra geometric way, right? I mean, you don't have any structure on this set, right? In some sense, right? On those orbit space.
No. It's just yes. It just gives representatives. Yes.
Yeah.
Yes.
So Galois cohomology will not give this information about the algebraic structure of the orbit space, right?
No. I don't think so. No, not all closures. You mean and things like that.
Yes.
No.
Okay, please, Diederik.
Oh, just a small question to the last point with the two-step nilpotent Lie algebras. We came across classification from these people Levstein, Kiraboshi using pencils. You probably know. I thought this would. There's already a classification more or less, but you want to do something more, I suppose, or.
I don't know. I don't know this. Maybe.
I mean, for dimensions 8 or 9 over real and complex numbers, I suppose you have at least these papers look like almost a classification by pencils and
I don't know.
Okay.
Yeah, maybe you can write me these names.
Yeah, Levstein, Kiraboshi. This is like communication of algebra.
Levstein, okay, I will look it up.
From 1999. And some related publications. So we had a paper on almost inner derivations where we are using this somehow.
Okay, because
but I don't remember how explicit this was.
Okay. I'll have to look it up. So what time is it published, you say?
In 1999.
1999. Yes. So we have a paper of Galitsky and Timashov about the same time.
Yeah.
Where they do it as also 1999. I see here now. Where they do this also using theta group. So that is our over the complex numbers.
Oh, I see.
So that is our. But I will look that up. Yeah. No, thank you. I will. Let's see.
Yeah.
Well,
and thank you for your nice talk, of course.
Oh, thank you.
Okay, any other questions? Okay, if not, let's thank Willem again.
Well, thank you.
Okay, and we will resume next Monday at the usual time. Goodbye, everybody. Bye.
Bye bye.
Ciao Willem, saluti anche in famiglia.
Ciao.
Ciao ciao.